Share screen, this one. Okay, good morning, everybody. My name's Johnny Someth-Darling. I'm one of the directors of the UK Urban Agritech, which is a group of farmers and researchers and suppliers who are trying to promote the climate-controlled environment agriculture industry in the UK. And I'm joined by Mike Ratcliffe, who's one of our members and sits on our advisory board, and he runs an organization called Aquaponics Lab, which well, he can tell you more about, but they make lots of cool stuff which you can find online. And I'm going to begin just with a quick introduction to controlled environment agriculture, taking you through some of the motivations for it and what the software needs are for farmers in the industry. So to begin with, if it lets me move. Okay, so why are we interested in controlled environment agriculture? Well, traditional agriculture has a pretty big impact on the environment. If you go to the, this is from Our World in Data, who summarized this information very nicely. Starting on the right-hand side, we've got a big impact on biodiversity. Like the vast majority of all the mammals in the world are there for us to eat or to eat the produce of. And that's obviously impacting the environment and pushing out nature, as it were. Growing crops is responsible for what's called eutrophication, which is when the nutrients from fertilizers get washed into rivers and into the oceans. This can lead to algal blooms, where algae soaks up all these nutrients, grows really big, and then it dies and it decays, and that releases a lot of carbon emissions and interferes with the natural ecosystem. We have a huge amount of fresh water use. Almost 3/4 of all the fresh water in the world is used in agriculture, and this is being diverted from ecosystems, so it has a negative impact there. We're using about half of all the available habitable land in the world for agriculture at the moment, and again, impacting on biodiversity, impacting on places we can live. And really, when it used to be a small amount, it wasn't so bad, but now we're really having a very large impact on the whole planet. And greenhouse gas emissions are agriculture is responsible for about 1/4 of these. And if you split that up, you can see that it is. Can you see my mouse? Yeah.
Yeah, we can see.
Yeah. Yeah, you've got the land use portion. You've got the actual emissions from the growing of the crops themselves, the livestock growing. That's all the burping and the farting from the cattle and things, and then the supply, the transport of this food. So these are all the impacts. And in controlled environment agriculture, we remove ourselves from the environment quite a lot, and we put ourselves closer to where the food is consumed. So we can affect quite a few of these areas. We can shorten the supply chain by growing the food next to where it is consumed. We can mitigate some of the emissions from crop production. We can definitely mitigate the land use and the emissions from that by growing the food in buildings and growing it in layers in tall buildings or in layers in a small building in what's called vertical farming. Most controlled environment agriculture techniques use a lot less water than traditional agriculture because it doesn't drain away into the soil. It stays in a closed loop system. And because it's in a closed loop system, none of the nutrients leak out, so they don't interfere with the environment in that way. So we can potentially have a lot of environmental benefit by growing more of our food in controlled environments. The other thing to think about is the human population is projected to grow by about 3 billion more people to a total of 10 billion in the next 30 years. And that means, if you look at this picture on the right, that means if we use conventional agricultural techniques, we would need a land area the size of Brazil on top of what we already have to be able to grow enough food for those people. And we don't really have that land, so we need some more innovation. Now, we need innovation in conventional growing, but I think that controlled environment agriculture can be a large part of that mix, especially when you consider that a large amount of this population growth is going to be in urban areas, and the actual rural areas are declining, so it makes sense to grow the food near where all the people are. On top of that, even if we stop climate change now, then we still have a lot of locked-in effects. So many of the areas where we grow food will no longer be able to grow food in a decade or 2 or 3. So that's even less space to grow on. And if we look at the current pandemic, we can see the effect of supply chains, or rather the inability of countries to cooperate on an international level with supply of scarce goods, like medical equipment in this case. But as climate impacts increase, we might find ourselves with a scarcity of food. And so if more countries can grow food locally in environments that they create rather than relying on the natural environment, then that might help everyone. So there's a lot of positives here. So if we're going to grow food in controlled environments, we need to think about what does that environment want to be like? What do plants need? And the simple model is in that picture. This is what we all learn when we're very young, that we need the sun, we need the water, we need the air, and we need the soil. And that's all true in a simple way. But the main problem with that is that it relies on the weather. And as we know, the weather is not a reliable thing very often, and increasingly less so. So if we take a more accurate picture of what is needed, we've got a list here. So water, sure, the water contains nutrients. Some of these are big ones like nitrogen, phosphorus, and potassium. These are the so-called macronutrients. But there are a whole bunch of elements that plants need in small amounts in order to grow to be healthy and produce good fruit. We need the light, as in the sun, and now all the plants in the world have evolved in the sunshine, which means the solar spectrum is well suited to them. But if you look at a plant is usually green. That means it reflects all of the green light, so we can save some energy by not bothering to use green light, and you can grow a plant just using red and blue. Although they do like small amounts of some of the other colors to help mature and be healthy. Gases are important, the atmosphere. So CO2 is the one that we all know about that plants use for photosynthesis. And but also plants need oxygen. They do respire with oxygen at certain times of day, so that's also important. We need conditions like humidity and temperature to be in the appropriate range. Obviously, a frost is very bad for plants, and if it gets too hot, they don't grow well either. And we need an appropriate medium. Traditionally, this is soil, but in controlled environment agriculture, we can use any medium we like, really, as long as it physically supports the plant. And we need to look after the plants, so we need to monitor them, make sure they're growing. If anything goes wrong, we need to change it. If the conditions are wrong, we need to change them. So how do we provide these in a controlled environment? We tend to provide, if we forget about soil for a moment, and we just think about delivering the nutrients through the water, as in solution dissolved in the water. These nutrients, when dissolved in the water, take the form of ions. So we can detect the presence of ions with electrical conductivity. We can check the pH level to make sure that is in the appropriate range. And if we want to spend a little bit more money, we can buy ion selective sensors, which will tell you more specifically which ions you have and which you need to top up. So you can always keep an eye on that as the plants are growing. Light can be measured in lots of different ways. The debate is always going on with this, but generally farmers like to use measurements which take into account which parts of the solar spectrum that plants actually use. So if you look at the little image here, you have the whole visible spectrum there, and you can see that the blue area and the red area are where the most of the photosynthesis comes from, but other parts of the spectrum are also important. So these measurements like PAR and PFF are designed to take that into account. The gases we would measure, if it's oxygen, it's like 18% of the atmosphere, so we measure that as a percentage. If it's carbon dioxide, which is a much smaller amount, we would measure that in parts per million. And you can buy cheap sensors which don't do a very good job for that, and you can buy expensive ones which do a better job of that. And plants often like more carbon dioxide than we do. So a lot of growing environments, they will pump in extra carbon dioxide up to around 800 parts per million sometimes. We're currently at 405 in the atmosphere. It would be nice if we were at 350. Humidity and temperature, as I said, were very, very important. Obviously, we measure that with thermometers, we control that with heaters, we can dehumidify the air, we can add moisture to the air if we want to. And all those factors, so those ones at the top, can all be combined together to create what people have started referring to as a climate recipe. And you can actually really quite accurately change the taste of your plants or the nutritional content, and just generally how fast they grow, how healthy they are, what they look like, by changing these parameters. And that's a very interesting area of research at the moment. On top of this, we need to provide a medium, which has to be the right shape and size for the plant. Some plants grow their fruit underground, some grow them on top. So all these things come into account. You might use different types of system depending on what plant you're growing. And monitoring is something that's also an interesting area of research now. It can be very simple. You can just look at a plant, write down how it looks, and write down every day and keep track of that. Or if you notice something is wrong with it, you can figure out what that is. But more and more people are starting to use cameras, using image analysis and machine learning techniques to spot, either it might be like how tall, what color the leaves are, how big they are. It might be looking at, like in this image here, it's quite small, but there's a computer algorithm identifying parts of the leaf which have been diseased or affected by pests in some way. And there's quite a lot of innovation going on in outdoor agriculture in this area at the moment. And there's a wealth of things generally that we can learn from data, both in the long term and the short term, to help our farming operations. Right, we're going to have a look at a few different types of hydroponic system, just give you a quick introduction to these. On the top right here, we have a very simple system, which is known as a deep water culture system, where you have a large tank full of water with nutrients dissolved in it, and floating on top is a sheet with the plants embedded in it. Very simply, just absorbing the nutrients from the solution and growing quite happily. There's often an air stone at the bottom, which is just basically creating bubbles to help to oxygenate the roots a little bit. Moving on, a slightly more sophisticated system is called nutrient film technique, or NFT. And you see, this is almost like the typical hydroponic system, where the water with the nutrients is pumped all around, and it flows in a very thin film just below the plant. So the ends of the roots are dipped into the film, but some of them are exposed to the air, which allows more oxygen to the roots, which helps the plants to grow a bit faster. And by recycling the water in this way, you use a lot less. To use even less water, you might want to use an aeroponic system, where they don't use a constant stream of water. They spray it through nozzles, so it becomes an aerosol. It becomes like a mist or like a cloud beneath the roots. And this allows the roots to get even more oxygen. You use less water, plants grow faster. But one of the problems with this is if anything breaks, if the nozzles break, then the plants may die within a few minutes. So you really want to have very good control and monitoring systems when you're using something like this. And then there are examples of more integrated systems using, for example, aquaponics, where they have plants and then they have fish, and they kind of exist in a circular relationship where the waste products of the plants will feed the fish and the waste products of the fish will feed the plants, although these are quite complicated and you do need to add and take away quite a lot during that cycle. But it's a nice thing that's, you know, approximates nature a little bit more. And here's some pictures of systems of various different sizes as examples of these. So here's a water culture system being lifted up to show the nice healthy roots there. We have a nutrient film technique system here, quite typical with rows and rows, saving lots of space, allowing all these lovely green plants to grow. And this is a vertical system which works in similar principles to that. Here in the middle, this is a really large aeroponic operation in New Jersey. It's a company called AeroFarms who've been doing very well in recent years. This is a huge warehouse, and they use scissor lifts and all kinds of automation to generate a profit and provide food to the local area there. And then on the bottom right, there's an example of a aquaponic system that's with a big tank of fish and some plants growing in the background, and the pipes will be connecting those two parts of the system. So in thinking about businesses that do this kind of growing, there are a few things to consider. Every year, well, since last year, there's a consultancy called Agritecture in the US who've been surveying farmers throughout the world and asking them many questions about their businesses, because this is still quite a new industry. And the number one biggest cost they encounter is the cost of labor, so the cost of their workforce. So this really implies that any advances in automation technology or anything that requires fewer people to grow the food is going to be advantageous, because this type of agriculture is still much more expensive than growing in a field. You can see here well, the majority of these businesses are in indoor vertical farms, which means we need to control the environment very closely, as discussed. And a large amount, almost half of all these farmers have had no experience in agriculture before this. So they're learning as they go. So the more we can do as software people to make it easy for them, the better it will be. To summarize all those points kind of up to now, I've got like 5 key features here of any urban agriculture software system would involve, you know, excellent data gathering and good analytical tools, faultless environmental monitoring and control systems, as much automation as possible, both to minimize the workload and to just to keep it efficient, from everything from monitoring crops to harvesting and packaging, anything like that. User experience visualization, very important for farmers who don't have a lot of time on their hands trying to run an efficient business. And connectivity of data and alerts generated from data, just in case anything goes wrong, is also very important. I'm going to just look at some of the main points of where we control and measure what goes on inside a farm. So here's a simple NFT system where you have the tank of water pumping the nutrients around, down 3 layers here. Each layer has its own lighting. And the various points of intervention we have in this system include the addition of nutrients, the control of pH levels. To some of the nutrients need certain pH range to be dissolved, and plants are tuned into certain pH ranges depending on how they evolved. We can control the flow of the nutrients. We can control the amount of carbon dioxide. We can add heating. We can move air around to prevent buildup of too much humidity, too much moisture in any part. Some of these spaces are quite small, so it's important to continually flush air through. And we can control the lighting spectrum, the lighting intensity, what type of lights we use as well. And then, of course, we need to measure all these things. So to measure the nutrients, as I said, we'd be using pH, electric current, electric conductivity rather, and ions with sensors in the nutrients themselves. We want to check the level of the nutrients. It will deplete over time, so that needs to be topped up. There's a little humidity sensor in here to make sure that's okay, a gas sensor, thermometers, and of course cameras, as I mentioned. So there's a lot of things to connect, and if we connect them all together, then hopefully we have a nice efficient system that doesn't require too much human intervention, except at the beginning and the end of any crop. And thinking about this, there's a distinction that's important to make between long-term data and very immediate urgent data. So the long-term data is like, how fast did my plants grow? How many tomatoes did I get this year? And you don't necessarily look at that every day, but at the end of a season, at the end of a crop, you might collect all that data and spend an evening looking through it all, thinking, oh, okay, maybe if I changed that here, maybe if I did this better, then the whole thing would be better next time. The other kind of data is when things go wrong, or it's the constant monitoring. So, you want to constantly make sure your nutrients are the correct, in the correct relationships, make sure you've got enough water, and make sure the humidity is correct, all these sorts of things. And in a very extreme case, if everything falls over, then you want, if you're not there, you might be at home having your dinner, and you want to know that your farm is collapsing, so you can go there very quickly and try to fix the situation. So yeah, we're making this distinction between critical needs and long-term needs, and the critical needs, basically that's everything on the day-to-day basis, and from these we can define what we call actionable data, which is the data that we need to take an action based on our critical needs. And then when we see that actionable data, we can then address those critical needs. So there's a kind of interplay here between those two important factors. Okay, so that's kind of the introduction. I'll hand over to Mike in a minute. But I bet you want to know what's inside this box. Have you all got one of these? Yeah, good. So we have a microcontroller, which you can see from the front and the back. That's going to do all our computation. We have a temperature and humidity sensor, which is the little purple chip in the middle. We have a servo motor here, which we can use to open and close the lid. And we have our USB, so we can talk to it. And there's also a Wi-Fi chip on the back. You can see the aerial there. And the Wi-Fi chip will allow us to communicate with the internet and send out some alerts, hopefully. So the project involves this sort of idea of actionable data. Like I said, we might be monitoring plant appearance. We might be monitoring nutrient concentration. But today we're going to look at the interplay between temperature and humidity and give us an actual number that is something our farmers would care about more, because humidity and temperature don't tell you the whole story. It's more useful in some situations to use a variable called vapor pressure deficit, which is calculated from temperature and humidity. And we're going to try to monitor that and to control it within the tiny greenhouse. Yeah, we have an equation here for how you can calculate this. Don't worry about that too much. It's in the code. And yeah, I think, Mike, do you want to take over at this point?
Certainly, Johnny.
Yeah. That's
Mike,
kind of
we
my
are
last.
just now sharing the link of GitHub you shared with us. So give us a second, and we will share the link with guys because not everyone received that.
Okay.
Just a second.
Supermarket? No?
Can everyone see the link?
Yeah. Yes.
You got it, right? All right, brilliant. Thank you.
Are there any questions, actually, maybe before any questions people have about anything to do with controlled environment agriculture?
Actually, I have one question because you showed us several systems, and how does it impact maybe how fast plants grow in each system, or it's not a big difference?
They all tend to be a bit faster than growing outside. Aeroponics, I think, is the fastest. Mike, you might have some more answers.
How much extra growth you get varies by crop to crop and what you're comparing to. At an extreme case, you can get up to 4 times the production volume, production speed. But if you think that outside is seasonal, if you take that into account and you're growing in a controlled environment and you can keep that consistent through the year, you can get 10, 12 times more growth.
That's impressive.
Yeah, so even if you're growing at the same speed, you're still growing all year round. That's the big thing.
Yeah. Any more questions?
I want to ask, how much does it cost to grow a single plant in a controlled environment?
A single plant of what? Sorry?
For your own needs, or?
Well, basically for your own needs, maybe one tomato plant or something.
When you're growing on a small scale, like an apartment or a house, the cost of your infrastructure can't be depreciated across that many volumes of produce. And the cost can be high if you are buying equipment, but if you're building your own, you can compete with the supermarket prices.
Yeah, I had a system in my flat a couple of years ago, a small NFT system with about 16 plants. And that probably cost me about £300, and it used about as much electricity as my television for 16 hours a day to do the lighting mostly. And that was, I got some good peppers and lettuce and stuff out of that.
Anyone else? Well, I guess we can move to the practical part then.
Cool.
Johnny, could you change the screen back to...
Oh yeah, sure, yeah, of course.
Grabbing. Excellent. Labadiana, everybody. Can I see the camera, Johnny, for the class? Are you hosting, by the way?
No, Alina's hosting.
Sorry?
That's better.
Oh, we have 2 cameras because one is intended to show closer when the guys will be doing the practical task and the others will be room.
Excellent. Before we start, can I ask who's got experience with microcontrollers? One. And the rest of you, pure software, no limited hardware use?
Yeah, basically.
Yeah. That's understandable. So we'll be using a very simple microcontroller and the Arduino IDE to program it, which is a type of C++, but with functions built in to make it easier to control the microcontroller. So most microcontrollers follow go line by line through your code, and you can get them very quick if you need to, or code them very easily and at the expense of speed. Let me share my screen. We'll go with screen 2. Can you also see? Can you see my screen now?
Yeah.
Yeah. So in the little box on your desk, you've got 3 main things in it. You've got your microcontroller, which is this Node MCU. As far as microcontrollers go, it's a bad one, but it does have the internet at an incredibly cheap price. So you get 1 analog to digital converter, 10-bit, and it's not a very reliable one. You get 16 digital pins to play with, 4 megabytes of internal memory, and the main one is the Wi-Fi at the end, all for a very affordable price. And also in the box is a BME 280, which is an air quality sensor. It measures humidity, temperature, and barometric pressure. And you can communicate with it through a few different protocols. The one in your box is communicating via I2C. Because it suits the speed requirements that we've got, and it's the simplest to implement. So you've got something, a microcontroller to program, something to measure the air quality, and you've also got a servo in there, which is to actuate. So I don't know if you're familiar with servos. Inside the blue housing on this motor, you've got a DC motor, a gearbox, and a potentiometer, which talks to a microcontroller inside the unit. So instead of implementing feedback loops and hard programming a motor, this has the logic inside. So you tell it what angle to go to, and it'll do its best to go to that angle and stay at that angle. And the way that we'll be programming the microcontroller is the Arduino IDE. For prototyping, it's the easiest option to go with often. Now, if you primarily because it's got libraries and functions which take care of all the heavy lifting. One function can be hundreds of lines of C++. And it just allows you to keep your code very concise. Now you can program it in C++ if you need to speed things up. What I usually do is I write the whole code in the Arduino language, identify bottlenecks which are slowing the controller down the most, and I write those in C. So as fast as needed only, is with as little work as possible. And we'll be using the Arduino IDE to program the microcontroller. It's relatively simple to understand. So you've got your setup loop, which runs once. Your pin mode tells you what mode to put your digital pins in. So if you want to power an LED, it needs to be high output current. So you set it as an output. If you was using it to communicate and you wanted to not sink a lot of current, you'd put it as an input, high impedance or low impedance. You've got your main loop, which runs indefinitely until you didn't anticipate a timer rollover or the power's cut. So we've got everything we need to control a small greenhouse now. We've got a microcontroller for the logic, an air temperature sensor, something to actuate the window open and close, and something to program it in. So this workshop will follow roughly the following routine. Setting up the Arduino IDE, we'll run through that quickly. and sketch what the first lesson we'll have is when you're prototyping a system, there's always hardware issues or hardware problems that you can fix with software. So you'll notice when you're programming this microcontroller, because we've got limited power from your USB on your computer, when the servo motor moves too quickly, it'll cause a brownout, which is the voltage inside the microcontroller's drop below the minimum level, and it's forgot what to do. So the first thing is to slow the speed of the motor down. We'll also decrease the baud rate of communication between your laptop and the microcontroller, and add some delays during and after motor movement, so we can let the power supply settle before we ask too much of it. The second sketch, we'll read the air quality sensor and calibrate the servo so we know when the window's open and closed. Then we'll control the window based on temperature. So if we'll set a set point. If it's higher than the set point, the window will open. If it's colder, the window will close. Now, you won't find these systems in a commercial setting past hobby level, but it will give us a very basic understanding of how to implement some feedback loops. Then we're going to cover doing complex maths on a microcontroller. So they're not like the microcontroller's ability to perform mathematics is very limited, and you need to think deeply about how you're going to implement any functions. So we'll cover how to do that with a limited microcontroller. Then we'll connect it to the internet. And then we'll test that we can use the internal memory, store the data, and store a little website on there in HTML.css files, a very basic web GUI. So this, over these 6 codes, we're going to cover testing most of the systems that are on the board, which is a good starting point for automation to test each subsystem. Have you all downloaded the workshop demos?
Yes.
Yes. If you open the PDF that's in there, so this one, and go to the 4th page. You've already downloaded the workshop demo, so we can skip that part. We're going to go to the Arduino website. And download the Arduino IDE for your operating system. Because I'm on Linux, it's showing me the Linux variants. I don't know what OS the rest of you are running. And I've done this earlier because here where I am in rural England, my internet is superb, and it would take all day to download the IDE. Can I have a hands up for anyone who's using Linux in the room? That's good. Makes it easier. Or a hands up when you've downloaded and installed the Arduino IDE. We've got the first one. Excellent. Now the next thing is the programming environment doesn't have the definitions for the board that we're using by default. So we will have to install the board definitions. Now all this does is tell the programming environment what the port mapping of the microcontroller and similar. So if you download if you copy and paste this link here, and we go to the Arduino IDE, we'll go to Files, Preferences, and you see here where it says Additional Board Managers. If you paste the link that you copied, which should look like that one.
Did you find everything? All good?
Yep, okay. And then if you go to Tools.
Just a second, Mike. You had a question, right?
What thing should I copy the JSON file?
Could you say that again, sorry?
That JSON file that you copied, that link that you copied into the clipboard, I didn't seem to find it.
Let me turn my speakers up.
That JSON file that you copied into the clipboard, where should I copy it from?
You copy it. Did you download the in the download file you did at first? There'll be a PDF called Greenhouse Control Lab Overview.
Yeah.
And on page 4, it is here.
Can you find it?
Oh yeah.
Page 4.
Yes.
Page 4. So you'll put it into Preferences, Additional Board Managers. And go to Tools, Board Manager. And into the search, if you type ESP8266, you should be able to install the reference for this microcontroller. If we could just get our hands up when that's done.
In Tools, Board, and Board Manager?
Yeah, let me run through that again. If you go to Tools, Board, and Board Manager.
If I have
And then in the search bar, you will type ESP8266, and it should bring this one up by the expressive community.
I have the Arduino app installed, so I guess I'll just install the Arduino program. With the installer.
Can you help him a little bit?
Yes.
Okay.
Is anybody else struggling in the room? Oh.
Can everyone find everything else? Yeah, all good?
All good. So now we've got the board directory in there, so the IDE knows what ports to write when we ask it to turn a pin on and off. We've also got to install the library for the temperature sensor, which all this library does is tell the I2C what registers to look at, what to ask for when we ask for temperature. So again, in the Arduino IDE, if you go Sketch, include a library, and then at the top, manage libraries. And then here in the top corner, you'll have to write BME 280. And it's the top one. Now, when you click install, it's going to ask you to install multiple libraries. Click yes. Has everyone done that? Just hands up if you're finished. Yep. Now, if anyone else is struggling, if you could ask the gentleman in the white top for help in Lithuanian.
Is your team finding everything? All good? If anyone needs some help, just ask.
Now, I believe you'll have to close the IDE and then reopen it. All windows once you've finished installing. So now we're in the Arduino IDE. If you just go to File, New, we'll create a new file. Now, the way that this works is it runs through void setup once, and it runs through the main loop multiple times. Now, as a tip here, whenever you're dealing with hardware and the Arduino, at the beginning of your code, put a delay of 10 seconds in. So the delay function here is measured in milliseconds, so 10,000 will be 10 seconds. Now, what this does is if you've got any corrupted sensors or bad actuators, they don't brown your board out as soon as you plug it in. You've got 10 seconds to plug your USB in and upload a better code. Otherwise, if you do experience a brownout through a coding error, you'll have to unplug all your sensors and actuators in order to upload a new code. So if we go to the top here, you've got verify. One second. If you go to tools, we need to select the board that we're using, and we're using the Node MCU 1.0. This just tells the IDE what ports to map to. So whenever you've wrote, it compiles the code every time that you write it. So this tick in the left-hand side compiles. So if you make an error, I don't know, misspelling delay, and you try to compile, it'll throw you an error up to say that you've missed a bracket. Well, it'll tell you what line your error's on. To upload the sketch, it's the arrow pointing to the right. And to communicate with the board afterwards, it's the serial monitor. So all this does, it allows the board to send you data. So if you can come back to the workshop demos folder that you extracted and go into basic sketch L1, when you double click on it, it should open in the Arduino IDE. I'll quickly run through this code line by line. If you go to the file page setup, you can add lines if you want. Preferences, sorry. So if you look at line 18, we're including a library. And what this library does is take care of the communication protocol between the microcontroller and the servo. So instead of manipulating a digital signal, the hardware, this allows us to just write just tell it a position, so it can go from 20 lines of code to a single line of code.
Mike, just a second. Guys who can't see, for whom it's too small, there's a live stream on Facebook, so you can go to Xplicity website, Xplicity Social on Facebook, and you can have the bigger view of code.
Sorry, is my screen not showing in full?
It's showing just.
I think the text is just a bit small, Mike, for people sitting at the back.
Okay, there we go. Better?
I can see it on the live stream though, so okay.
Is it more convenient now, like this? Yeah? Okay, good. Okay, problem solved.
Now, if you read the top here, the comments are started with 2 forward slashes. So this just explains what this library is doing and what these variables are. So because I made the wooden housing that you can see in front of you, and I made it incorrectly, the motor will foul on the housing if you allow it to turn too far. So here you can see I put a max and min position, which keep the servo motor in a safe position, independent of what you ask it to go to. So if you upload that code now, compile it. You'll need to go to Tools, Port, and select the port that you'll have to plug the device in and then go to your port and select the USB port that it is. So that's just telling the IDE what USB device to program. Is everyone's unit moving? Right, what you might experience now is if you come up into the top right corner, the serial monitor, you'll be able to see the code which I've already put on the device, well, the output from the code. When your window opens, select a baud rate of 115,200. Has everybody been able to do that? Let me plug my device in. So you'll have to tell the IDE which port to use. So here it's USB 0 for me. And if you come to the top right of your screen, you'll have a serial monitor. And you may not be able to open it. You may well be able to open it. Spare me a second. I'm on Linux. I've got to add...
On Windows, the ports come up as, mine is COM3. It's usually common in a number, I think. I imagine Apple's probably the same as Linux, but I don't know. That one's moving very quickly.
Johnny, could you... just 1 second. You're on Windows, aren't you?
Yeah.
Aqua. I won't be 1 second, gents.
Oh. Mine looks like this.
Are you on the screen now?
No.
Could you grab the screen there?
Sorry, what, Mike?
Could you share your screen just for a moment, Johnny?
Oh yeah, sure, I can do that. You have to let go of it, I think.
Okay.
What do you want me to share?
If you could just open the serial port.
Okay. The serial monitor, or?
Yes, the serial. If you could connect to the serial port from tools.
Tools. Tools port COM3 is what I've got here.
Yeah, I've just got mine. I've added the USB to mine now, Johnny. I can grab the screen back.
Okay.
Thank you, Johnny.
All right.
So yeah, we've got the open here. If you go to Tools, select your port, and then open your serial monitor. I believe you'll have to go to 115,200. And you should get an output on the screen on your serial monitor. That tells you the temperature. Is that happening? Did you say yes then, sorry?
Yes.
Excellent. So what you may find now is that this serial window keeps dropping out because you're experiencing brownouts. Your voltage is dropping too quickly on your USB line. So this sketch L1, we fix that by slowing the communication between the microcontroller and the PC down to 9,600. And we create a function to move the servo more slowly. So what this function does is when you ask the servo to move, it moves 1 degree and then delays by so many milliseconds that you've defined. So if you click upload with this code, you should have an output at the bottom like that, writing a certain address on the controller and a percentage. And if you open the serial monitor again, you'll have to change the baud rate to 9,600. And I'm and if we look at the main loop, we're printing to the serial monitor how many milliseconds the controller has been powered on. We're reading the temperature sensor and we're making the servo move, and then we're delaying by 5 seconds. So in your serial monitor, you'll only get an update every 5 seconds. Now, can I have a hands up for everyone who's getting a temperature, who's getting the readings for the sensor? Only one? Are there none of the rest of you getting readings through the serial window. If you go to Tools and Port, is your port still selected? So reselect it and then open your serial. And some of you should be change this baud rate to 9,600, the new slower one that we chose for better communication. Are we now getting readings through the serial?
Yeah.
Could I have a hands up if you're getting readings through the serial? 1, 2. Could somebody who's not getting readings put their hand up? Okay, gentleman in the black top, hoodie. What problems are you encountering?
I'm currently uploading the program, so it's just a matter of waiting, I suppose.
And did you upload did the new code upload successfully?
Yes, I'm uploading it right now.
Right now.
What temperature is it in your room, everyone?
33 Celsius.
23.
Open a window. I'm 29.
Mine says 31 and a half. I don't really believe that.
Don't forget, Johnny, it is in a box.
Yeah.
So after you uploaded the code, did the serial monitor open and give you data? Yes, excellent. So all this code really does, if we look at the main loop again, it prints the uptime to the serial, it reads the sensor, moves the servo, and then does nothing for 5 seconds. This is just a basic test to check that your hardware is working. If you come back to the workshop demos, we're now going to open Sketch 3.
You're skipping number 2 there on purpose.
I'm going to see what number 2 was. Yes, I'm assuming that all the units are calibrated similar.
Okay.
So if everyone's got basic Sketch L3 open, in this sketch we start to implement a temperature controller. So if you know the temperature in your room to be 33, I believe you said. If you change this set temp variable to 34, this is the temperature we're asking the mini greenhouse to maintain. So if it's above 34 and the band gap, the window will open. If it gets below 34 minus the band gap, the window will close. We've told the servo as well what its closed position is in degrees and what its open position is in degrees. And down at the bottom is our hysteresis control loop. So that we call this function from the main loop. After we've read the temperatures, we compare the air temperature to what we want it to be, and open the window if it's too hot, close the window if it's too cold. So again, if you go to Tools, Port, and select your USB, and upload the code,
An error of redefinition of servo, Windows servo.
pardon, could you say that again?
I got an error saying redefinition of servo, window underscore servo.
What line did it? If you go to File, Preferences, and Display Line Numbers, and then compile it again, which line did it tell you?
Not sure. Preferences and
File, Preferences, and just here, Display Line Numbers.
it's in line 34.
34. And you're on basic sketch number 3?
Yes. Yes.
Does your code look like the one on the screen now at line 34?
Yes, it's exactly like it.
And it's throwing you an error. Johnny, could you compile that on your Windows machine?
Yeah, I have done. It's working fine.
Could you close L3 and reopen it just to double check it? You didn't catch a keystroke when you opened.
What did the error say? What did it say about the line?
Redefinition.
Redefinition. Oh, I had that problem, didn't I? When we tested this.
And is it still showing you the same error now?
I'm uploading. Yes, it does. And now it's in redefinition of void set.
Of what line number does it tell you the error's occurring now?
4.
34 still?
64.
Oh,
64. I threw you the same error as well, Johnny. If you could just close the whole IDE down No, all the Arduino windows. So, boom, boom, and then relaunch the Arduino again. I don't know why that problem's appearing just on your machine, but Johnny did have a similar issue.
Yeah, I think I just had to close all the other windows. I think.
Yeah, how do I close the tab?
Pardon?
How do I close another tab?
Sorry, the microphone's a little noisy there. How do you?
How do I close another tab? I have. You don't need to close all other. And all that.
Yeah, close all the Arduino windows. So if you Alt-4 on all of the all of the Arduino.
Yeah.
You're essentially choking the Arduino IDE to death, and then you're going to revive him to see if he's still got the issue.
Yeah, I do that, and it says the definition of void setting.
Borrow me a second. Line.
It's line 64.
64. Void setup.
Okay.
Is anybody else experiencing the same issue? If you could raise your hand if you've got the same issue.
I have another question.
Please go ahead.
Is the lid supposed to close when the temperature is higher or lower than the set temperature value?
It's not closing when the temperature's above or below. No. Okay, so if you come down to the control,
it has to be above or below by half a degree before it changes.
So if you look at line 216, you've got the if statement. If air temperature is above the set temperature plus the band gap, then open the window. So what was your set temperature?
Mine was 34.
And what temperature do you have now?
That's 34.
Still 34. Once it gets above 34.5, it will open. Now, the reason that we had a band gap like that is to reduce the amount of times that your greenhouse windows are opening and closing. So if you only had, if air temperature is greater than your set temperature, the window would open, the temperature would immediately go down, and the window would close, and your windows would just be opening and closing. They'd be acting more like fans than windows. So you add a band gap of 1 degree so that the air temperature needs to drop by a degree before the window closes to reduce the duty cycle. It'll make your motors last a lot longer. on a commercial greenhouse. Now, the gentleman who was getting the errors, are you still getting those?
Yes, I am.
Could you put your hand up, because I can't recall. And are you using the Arduino IDE?
Yes, I am.
And what OS are you running? Windows, Mac?
Windows 10.
Windows 10, and it's Arduino 1.8.13.
Yes, 1.8. Yes, it's the exact same version.
Is it relatively simple to reboot your computer?
Yeah, quite alright.
Because I've got a feeling this may there's nothing in the code of there's no read definitions in the code itself. So I'd imagine it's a IDE problem. Now, are people's windows opening and closing at the temperature they set?
I think this team is also having some issues with some lines, but maybe you can tell what exactly should you experience.
Yeah, I'm getting these and some others are not declared in scope.
Let me change my internet to my phone to see if that clears the signal up. My line may drop for a moment here, gentlemen. Gentleman in the red top, could you say what issue you was having again?
Me.
Yes.
I'm having these bits was not declared in scope and some other variables.
Could you in the text box write down the question, because the signal's a little hard to understand.
Caps. Put this in your soon.
D6. Right, for that, what line does it give you that error on? I'd imagine line 70.
Yeah, it's line 70.
Tools, board. If you, in the Arduino IDE, go to Tools, Board, and select the Node MCU. So how we, at the beginning, we loaded the board definitions up, and that D6 corresponds to a digital pin on the board. So we just need to tell it that we have to tell it which board to use. Do you understand that?
I think so.
Which version of Node MCU should we select?
1.8.
Yeah, that's
I think it's working now.
Yes, so if you your serial monitor, do you get and select your baud rate at 9,600? You should get an output like this.
Can you find it?
Where do I find the serial monitor?
First, if you come to Tools, Port, and select a USB port, the COM port, yours will say. And then in the top right of the IDE here, you've got a micro magnifying glass.
Yeah.
If you click that, a window like a window should open. You will have to select your baud rate to 9,600, and you should have a similar data.
Yeah, it's working. Cool.
Excellent. Is everybody else's working, or have we still got errors?
Working.
Could I have a hands up if you're not getting a readout on the serial, or if you're a little bit behind? Oh, so we're all going.
what do I do after I select the board Node MCU?
Have you uploaded the code? So you select the port, you upload the code with this arrow button here in the top left. And when it's down at the bottom here, you'll see it's writing the data to the program to the board.
Yeah, it's done.
It's done. So your greenhouse may make a rapid movement, and then you open the COM port here in the top right. you may have to reselect your USB port. And you're getting a readout on the serial, like on the screen? Excellent. So what this little experiment does, what this little code does is open and close the windows based on temperature. Now, has anybody seen the windows open and close? We've got one in the back. The gentleman in the white top is yours. Is yours? Yes. It's controlling temperature, roughly.
It's controlling temperature.
Yeah, excellent. So that we've done with that sketch there. If you go back to your folders, you've got your L4 sketch. So now we're going in this program. It builds on the last one, but we're going to calculate the VDP, vapor pressure deficit of the greenhouse, which is a representation of how well the plant breathes. So on the bottom of the plant's leaf, it's got valves that control gas flow. We want those stoma or valves to be fully open all the time, so it can breathe to the best of its ability. So if you, in your code, if you come down to...
Mike, just remember you have to change the temperature again, everyone, the set temperature.
Yes, if you want it to control temperature, you'll have to change it again to whatever it is in your room, plus a little bit. All I'm going to cover in this one is if you go to the bottom of the L4 code and go up a little to line 191. Here we're calculating the VDP, and it's quite a complex calculation for such a microcontroller. So you've got to be relatively careful about the way that you implement the calculation. So if you're ever multiplying by a whole number or using a whole number, say 100, if you add a 0.0, it increases the precision of the microcontroller. Another another issue with microcontrollers is they don't, if you try and divide by 0 by mistake, say you're reading humidity and you get a 0 reading and you try to divide by it, it's got no error checking to stop against that. It just falls flat on its face. It gets stuck in the same place. So when you're implementing mathematical functions on an Arduino or microcontroller, be cautious about how you implement it. So if you upload this sketch, Has everybody managed to upload that sketch?
Yes.
Yes.
Excellent. So make sure your port's selected again, and if you open the window, if you open the serial monitor, we should now be getting a VPD reading, which is measured in kilopascals. Now, to a farmer, this VDP value is more valuable than temperature and humidity. So in the workshop, in the overview PDF, the last page explains vapor pressure deficit, not that you need to understand it now. But you've got, a farmer will be looking at a chart like this. So up in the top right, you've got three different values for your VDP, depending on the age of the plant. So is it a young plant, an old plant, or in the middle? And you want to, when you first start your plant, you want your VDP to be lower. So in this green band here. So your plant will grow pretty much the same at 60% humidity, 15 degrees C, as it would at 34 degrees centigrade humidity. So in a greenhouse, the temperature changes. We can't control it. We can control humidity. Sorry. As the seasons change, your greenhouse will change in temperature, your maximum temperature. Instead of trying to control the temperature, because it costs a lot of money to heat a greenhouse, we control the humidity and keep the humidity in, keep the VDP in this green bracket for plants that you've just planted, and for middle plants in this bracket, late plants this. If you get into the red side, your plants won't grow and they'll be damaged. Not only will your volume go down, but the quality of your plant will go down. So you'll get less, and more will end up in, more will be returned from the consumer. So your VDP is much more important than your temperature and humidity alone. So you've got a little controller now which is showing you your VDP, which is 2.76 for my location. Can anybody tell me it at yours?
4.05. Yeah.
4.05. Your plant, if that was a greenhouse, your plants would not be doing very well. Mine wouldn't be doing too well either. So as far, the next lesson that we're going to cover is the L5 sketch, which is where it gets a little bit more interesting for those of you which are more used to the internet side of coding. So if you open L5, we now connect the microcontroller to the internet, to your Wi-Fi, sorry, there if it's available. So up at the top, you've got your IoT variables. Line 29, you need to change to the Wi-Fi name in the room. It's case sensitive as if you was putting it in your phone. And the password as well, so password. You need to change where I've got Farm B to your Wi-Fi the name of your the Wi-Fi in that room or in that building. And the password for your do you have the password, the Wi-Fi name and the password?
Yeah. Yes.
Yep. Have you entered them into the code?
Yes.
Excellent. So the way that what this will do is from our void setup routine, we call a function to set up the internet, and then from our loop, we check if there's anyone connected to that IP address. So in the setup routine, the libraries that we're using make connecting to the internet relatively simple. So on line 277, because I've not got a Wi-Fi password here, you just call Wi-Fi begin and give it your SSID. And that's it. Your router it'll connect to your router and be allocated an IP address. And then we we tell it to begin its server, and we ask it what IP address it's got on the router, and print it out to the serial, so we can look in the serial monitor and say it's at IP .112 at the end. And when we check the internet, if you come down right to the bottom of the page, client print is what we send to the user connected to the IP address. So this is a really awkward way to write a HTML document, sending it line by line. But that's what we're doing. We're sending it. We're sending the user a HTML page. So you've got your header, a variable, and it's a very simple web page. If you upload that code now, and see if you figure it out. I'll be back in 2 moments. Right, has everybody managed to upload that code? Right. What might happen now is, because we've tried to connect 12 devices all at the same time, we might have run out of IP addresses on the router, depending on how busy the establishment you're in is. Don't be dismayed if it doesn't give you work straight away. And can anybody tell me their IP address for the microcontroller now?
192.
if you go to Google, to Chrome or your web browser of choice and type the IP address in, does it tell you anything?
Yep.
And what is it showing you?
Temperature, pressure, humidity, and pressure depth.
BDP, yes. So hopefully mine will show me the same thing. So I'm at 13. Just 1 second. So if you take a look here, my unit's at 13. And now we can access the data from anywhere on the local network. Is everybody getting an IP address allocated?
Yeah.
Yes, excellent. So the Elena, sorry. How long have we got left in this workshop? Excuse me. How long is left on the workshop, John?
Oh, I think we started. What time did we start? It was 12, so we had 2.5 hours. We had 2.5 hours, so we roughly have 40 minutes. With
40 minutes, excellent. That's enough time to cover the next section. So if you want, now we've connected to the internet, we know that the Wi-Fi on the chip's working, we can do a little bit more with it. So if you go back to the workshop demos and go to Sketch L6, you'll notice that this folder looks a little bit different. We've got the Arduino Sketch, and then we've got a data folder. So if you take a look in the data folder, we can upload that data folder to the memory on board and put a full website on there locally. I think this one's made with Bootstrap. You've only got 4 megabytes to play with, so you're not going to be writing a very fancy web portal, but it does increase your ability to add graphs and charts and make it look nicer and open up more of a user experience. So your index file, if you open it with a text editor, just looks like any normal HTML file. We're running we're running some JavaScript functions in the and you can build that like you would build any other website. But because the memory on this board is not on the chip itself, we need to download another library to be able to access the memory chip, which is on board but external. So if you come back to the workshop PDF that we got, we've got this link here, installing the file system uploader. It should open this website, and we go to the release page, follow the links, and we download the zip file. Once you've got that file downloaded, you'll have to unzip it. Yep, you'll have to unzip it to your downloads folder. And from the IDE, we need to manually place this in the tool system for the IDE. So if you go to Sketch and Show Sketch folder, it won't take you to the right place. If you open File and Preferences, it'll tell you your sketchbook location, which in my case is Home, Aquaponics Lab Arduino. Nope. You need to find out where your Arduino software was downloaded and installed. So on mine, I've got it in a separate folder. And when you get to this, you need to open your tools directory and paste in the extracted file from your downloads that we just completed.
Where do I put it again? The file? Which folder?
Which folder? If you go, have you got a hot link for the Arduino IDE on your desktop? Like
Arduino directory, but
because I'm not familiar with Windows too much. Can you see where that exe is downloaded to? Where it's placed on the hard drive?
in that place right now.
So you should have a folder that looks like this.
1 second. I think I figured it out.
Pardon? Johnny, where is it on yours, buddy?
I'm just looking.
You're going to have to do this as well because we didn't go through this one.
Yeah, I need the. Can you show me the link again? I don't have the PDF. Can you just show the link again? I just typed something in wrong.
I don't believe I can, Johnny. I've shut my. Oh no, yeah.
Or paste it in the chat or something. There we go. Okay. Thank. Oh, cool. Thanks, mate.
No problem. So once you can find out where your folder is, where your Arduino ID is installed, you'll have a folder called Tools. So you go to your downloads, you select your unzipped file, and you paste it into your tools. Is anybody struggling there or not found it yet?
Anyone
have a
have
hand up.
questions or difficulties?
Okay, so you've all got it you've got it downloaded in your tools. Johnny, are you up to that stage yet?
No, I'm still searching for the location. But okay, go ahead.
I think if you right click on your shortcut on your Windows, it should show you your location.
It doesn't from start menu, and I don't have an icon.
Oh, you've not got it on your icon. No. I wish I could be more help, John.
That's fine. I'm just doing a search through the file manager.
Okay. So once we've got that, the next thing we need to
Mike, the connection is very bad.
install is here.
You can barely.
Sorry. Next, we need to go to this link, which is coming through the chat as well. So we're sending data between the website and the microcontroller via WebSockets. We need to install a library for the WebSockets to make it easy to use. So it should open in a new window. And if you download that zip file from GitHub, you will come into your Arduino IDE, click Sketch, include a library, and add a .zip library. So when you click that button, it will open up a file browser, and you just go to your downloads and click on the WebSockets master.zip. I got an error because it was already installed. You shouldn't.
Sorry, Mike, what was the menu sequence for that zip install thing?
Just let me open the... no, if we open out Sketch L6, I'll show you now, Johnny.
All right.
We go to Sketch, include a library, and add a .zip library. And then you navigate where you downloaded the WebSockets.
Yeah.
That one, and click OK.
Thank you.
Now, once you've done that, Johnny, is it gone through?
Yes. Sorry, can you tell me which thing I need to download on that first link from the first GitHub page? Which there's a few different things there.
You install the top
one.
You've come to this web page and then gone to this one. You download the top one here, Johnny.
Cool.
You'll need to unzip it.
Yeah.
And then copy it to your navigate to your Arduino location.
Yeah.
Go into tools and just paste it. It shows up like that. So you'll have ESP, Mangle, Wi-Fi.
Thank you.
Now, if you click compile, it might work. You might need to restart the IDE. I'm not too sure. And click upload. John, are you okay? You're very pretty, but I can't see the glass.
Sure.
Right, so has everybody uploaded the code?
Yeah.
Did it come, now that it's uploaded, if you open it again, it should give you the same IP address as before because the router's stored. Give you a static IP for a few hours, I'd imagine. And if you, again, open your browser and go to the IP address, it should show you absolutely nothing. Is everybody getting a blank page now?
For some guys, it's still being compiled, so let's give them a couple more minutes.
Okay. So when you open your IP address, you should get the same error message that I get, and that's because we're not uploading an HTML file line by line anymore. We've uploaded it. We're sending it one which is saved to the memory on the chip, but we've not yet put the file onto the memory. So if you close your serial monitor down and you come to tools, you should have a section which says ESP8266 data upload, which is a separate function that sends the data file the data folder we looked at earlier to the microcontroller. Has everybody managed up to speed, or is some lagging behind?
No, I can't find that option.
Okay, so what did you close the Arduino IDE and open it again after following this step?
I do. So I guess I'll do that now.
Does it now show you that option?
Do I have to upload the code again when I reopen it?
No, when you go to this option here, the data upload option?
No, I don't see it.
Okay, we've probably, did you download this file from this step, sorry? This,
Yes, I did.
If you come down, it'll take you to the GitHub page, this GitHub page.
Yeah, I downloaded it.
You've already downloaded it, did you say?
Yes.
Yes. Did you copy and paste it into your tools folder in your Arduino folder?
Yes.
Does it look like this, or is it still zipped?
It looks like this pretty much. Can you open the ESP file folder? Oh, great.
Is that what is it still zipped by any chance, or?
No, it's not. It's just that I think that you have a folder inside that folder, and I removed one layer of folder.
No. If you could do it so it looks like this.
I mean, the name of the folder is a bit different, but it's the same.
What's the name of the folder, sorry?
Arduino's -ESP826666 and that's something plugin method. Yeah.
And did you change anything then that you saw that was wrong?
No, this time I didn't. I just uploaded it.
Because have you got multiple instances of the Arduino IDE on your computer by any chance?
No, just one.
Just one. As the gentleman in the white T-shirt, do you see the data upload option?
Excuse me, what? And where exactly?
On Academy.
I mean, I got it to work, so yeah, probably. Sketch data. Or.
Sorry, does
Does
it look like this one?
Yeah, I see it.
Yes. Could you help your colleague to see if you can see what the issue is? I think my accent can be hard to understand.
You had exactly the same view as he does now? You had exactly the same view as he does now? When you start working on your PC?
Yeah.
Johnny, by any chance, do you have the option showing?
No, I haven't got it. I've got. Can you show me this folder structure again? If your Arduino libraries.
Yes. Is my screen still showing? Yes. So you find where your Arduino. Yours will look slightly different on Windows.
Mine is a bit different. So I found the secret location, but there's no tools folder there. And then I found the libraries location, which is just in my documents and like folder, and that's where all the other libraries seem to be. And I put it.
No, sorry, Johnny. This is not a library for the microcontroller. It's a library for the IDE itself.
Yeah, so I'm looking. There's no libraries.
If you do one step back, can you find tools?
Well, no, it's not like that here.
Maybe you can search for Wi-Fi 101 folder.
Yeah. That's not in there.
Maybe you can ask some questions and I could help.
So have more of us got the... Can you put your hand up if you get the sketch data upload option? Right, if you upload the data, upload and then upload the sketch normally, go to the IP address, you should see a splash page with a little bit fancier CS with a bootstrap based GUI.
Is that working as it should? Yeah.
Johnny, are you looking at this, my screen now?
I am, yeah.
Step 2, this PC document programs Arduino tools, it should be.
I looked there. Oh, no.
How's it going there, Johnny?
Yeah, no, my computer doesn't look like that. It's funny because it's not in all the normal places. If everyone else has got it, just go ahead.
Yeah, so has everyone got the, just let me check. If you go to the IP address it gives you.
So do you have the same results?
So I've gone to the IP address that it gave me, and this is what you, is my screen still showing? This is what it should be showing you. You've got a heading, a logo, which would be any logo, a button which refreshes the readings. We've been saving the data as a in a CVS format, so we can download the data. And that's not what it should be saying. So yeah, if you open the data in Excel or similar, you can see here we've been logging the data. There's no timestamp, which I recommend putting. But later on, if you ever want to look at the data for the whole year or build a graph, this is your CVS data that's saved to the memory, can be used. You can delete the log file, and just a little button to open a window with the chart because it's useful to the operator. So again, this is a very basic GUI, but it's got a little bit of everything you need to build a better one. So you've got you've got not only the HTML files and the CS, the style sheets saved locally. You've also got the transfer of information via WebSockets as well. So the basic building blocks for building something better. I must apologise for the quality of this code, this final one. It's a copy and paste from a project I worked on quite some time ago. So quite a lot of this may well not be needed. I won't be 1 second. Apologies about that. So has everybody managed to upload the files to the onboard non-volatile memory?
Yeah. It tells me that Python was not found.
Sometimes you just get a very unlucky computer. So it's told you your Python's not found.
Yeah.
But you have now got the option to data upload.
Yes, I do.
That may well take some digging to get to the bottom of. Maybe you've changed your Python version for another bit of programming that you do.
No, I don't code in Python. Should I download Python?
Is anybody else having the same issue? Could you take a look at one of your colleagues' computers just to see what it looks like when you've got the data uploaded? So it's looking more like a web page than the first example we gave, and you can put style sheets in the memory. You can put quite a lot of functionality in there. So that brings us to the end of the demos. We've tested every system, every subsystem of the microcontroller, verified it's working. It needs so a very basic proof of concept. Before it goes into a commercial setting, there's quite a lot of refinery that goes on and real world testing. Like you wouldn't want to put this code in a greenhouse. It's not been tested. So, do you like the web page, Johnny?
Yeah, the web page is lovely.
Yeah, and one thing I forgot to mention is the board that we are using in this example is around €4 to €5, so it's a very cost-effective microcontroller that can connect to the internet. It's used by makers and also commercial products. The quality of the code is the only difference. So, are we ready to open up for questions, Johnny?
Yes.
Excellent. I shall stop sharing my screen. So yeah, no doubt there will be some questions.
Anyone has some questions?
How long have you been doing with Arduino and hardware?
You mean preparation to start or what?
How long have you been working with hardware like this?
How long have I been working with these boards?
Yeah.
I'd say this particular board around 5 years. But the code, which these demos aren't representative of real world programs. They were made very quickly without much checking.
And what did you find the most challenging in that path?
More on the hardware side. So microcontrollers are, the datasheet for this microcontroller is actually really poor compared to one from Atmega or Atmel. You have to do quite a lot of testing yourself. For example, on a normal microcontroller, they'll give you the resistance of the digital pins as a stated number, whereas this microcontroller does not come with that information, and you have to calculate it yourself using a resistor and a multimeter, essentially. Same with rise time and fall time with digital pins. You need to work it out with an oscilloscope. So there are drawbacks to using this particular chip.
Yeah, thank you. Any other questions? use your chance.
Well, I hope you enjoy the boards now are quite useful for playing around with. So you've got a IoT MCU to play around with in your free time if you want.
Well, at least I believe people could try that before, have the primary impression how everything is done.
Pardon, could you say that again?
At least people who never had experience with IoT and hardware connecting stuff have the primary impression how it's done.
Yeah. So working with hardware can be challenging if you're coming from a pure software background. I came the opposite way. I came from a physical, mechanical background to a coding one, and no doubt you've got the same learning curve I have in reverse.
Yeah, I came from I was an electronics undergraduate, and then I ended up playing around with these things with Arduinos, mostly because of music applications and stuff like that, MIDI controllers and things like that. This is, I think, like what Mike's written on that code is much nicer than anything I've ever done in terms of proper using source files and not trying to do it all yourself and actually making something that works.
I would like to re-stress the point with the Arduino IDE. It makes programming very easy, but there are, if you want, there are certain routines and functions which are too slow for real world use, and you'll find yourself rewriting them. But you only need to rewrite, say, 5% of your code in C++ to make it quicker, and 95% can stay human readable Arduino language.
All right, I guess so. If nobody has questions.
So I have no questions. So basically, as I understand, the Arduino language is written in C++, right?
It's very similar to C++. So if you look at some of the functions that we're calling, for example, serial print or digital write or delay, ignore delay. Digital write, for example, which is the turning on and off of a pen. If you look at what function that calls, that's written in C++. But it's got a lot of overheads in there to sort of idiot-proof it. So it double checks that it does quite a lot of checking before it writes the pin. So instead of just controlling one port of the controller and 2 lines, it might be 20 plus lines of code to achieve that in the background. So as you dig deeper and deeper, it's C++.
And why is it C++? Use something that's easier to write like C#? Is it because of speed and performance, or is there another?
Microcontrollers are very relatively well established, and we have picked up. There's quite a lot of legacy in there when it comes to programming language and techniques. So you may find it's actually C deep down.
Yeah, probably is. I think a long time ago, people wrote really nice compilers that went from C to machine code, and they haven't bothered to do ones beyond that, I think. Is that right?
Yeah, with this particular board, there are options for writing the code in Python and other languages. But from an ease of use point of view, I find the Arduino language is the easiest, despite knowing Python.
All right, so I guess that's more or less all we wanted to ask.
Great. Thank you very much. It's been fun.
For the time for preparation and for forts. It was really brilliant.
Cool. Thanks, Mike. Good job.
Indeed. Thank you very much.
Bye, everyone. Enjoy the greenhouses.
Thanks. Have a nice day. Bye.